It's the longest bridge ever built, stretching an impossible 164.8 kilometers across China's floodplains and lakes, a structure so vast that, by all common sense, it shouldn't even stand. Every engineer knows, for each extra span, the risks multiply. Soil that swallows support columns, fault lines ready to crack concrete, typhoons strong enough to tear steel and lift loads from thousands of speeding trains. By traditional logic, this record-breaking bridge should already have failed. So why does it defy the odds? And what hidden choices let it survive day after day? The answer isn't a single miracle, but 1,000 invisible defenses you've never seen. And everyone is about to be tested. The title of longest bridge is less straightforward than it seems. Different authorities use different yardsticks, and the record can shift depending on how you measure. The Danyang Kunshan Grand Bridge in China holds the Guinness World Record for overall length, stretching 164.8 kilometers across the Yangtze River Delta. This measurement includes every elevated viaduct, approach ramp, and segment, whether the bridge crosses water, marsh, or dry land. By this metric, it is the world's longest bridge, nearly 4 times longer than the English Channel itself. Other bridges claim records by focusing only on certain segments. The Lake Pontchartrain Causeway in the United States, for example, is often called the longest bridge over water, at 38.4 kilometers of continuous span above the lake. The Hong Kong, Zhuhai, Macau Bridge, at 55 kilometers, is promoted as the world's longest sea crossing, combining bridges, artificial islands, and a tunnel under the Pearl River Delta. Meanwhile, the Akashi Kaikyo Kawayo Bridge in Japan is recognized for the longest single suspension span, at 1,991 meters between towers, a feat of unsupported engineering. There is no single technical standard. Some lists count every approach and elevated segment. Others count only the main span or uninterrupted water crossing. National governments and engineering bodies often choose the definition that best highlights their own achievements. For China, the Danyang Kunshan Grand Bridge is a symbol of scale. 164.8 kilometers of viaduct, supported by more than 9,500 piers, carrying high-speed trains at up to 300 kilometers per hour. The bridge connects the cities of Danyang and Kunshan, threading across floodplains, rice paddies, and open water. Choosing this alignment was never about chasing a record. Engineers weighed every alternative: tunnels, causeways, ferries, and found each one lacking. Tunnels at this scale risk leaks, ventilation failures, and massive upfront costs. Ferries mean delays, weather shutdowns, and limited capacity. Only a continuous viaduct could deliver the reliability, speed, and year-round operation demanded by China's high-speed rail network. The result is a bridge that redefines the very idea of crossing, a structure so long that, from end to end, the earth itself seems to curve beneath it. A viaduct was not the obvious answer. On paper, a tunnel offered shelter from storms and ship collisions, but the Yangtze Delta's soft soils, high water table, and shallow bedrock made deep excavation hazardous and expensive. Ventilation alone would require vast shafts every few kilometers, and any fire or blackout could trap thousands underground. Ferries, once the lifeline of the region, are no match for modern demand. Each crossing is at the mercy of fog, typhoons, and river floods, with hours lost to weather shutdowns and maintenance. Even a causeway, solid earth embankments across the marsh, would block water flow, disrupt fragile wetlands, and quickly erode under the relentless current. The viaduct, a continuous ribbon of concrete and steel, offered speed and certainty. But this choice unlocked a new set of dangers, multiplied by the bridge's record length. The entire route sits atop delta soils prone to settlement and liquefaction, especially during floods or earthquakes. Land beneath the piers may sink or shift, twisting the structure above. Active seismic faults cut across the alignment, threatening sudden ground movement. Typhoons sweep in from the East China Sea, bringing hurricane-force winds and waves that test every span, every joint. Rivers flood with little warning, scouring away the ground around piers and foundations. The risk of ship collision is ever present as barges and tankers thread narrow channels beneath the bridge. Temperature swings of 40 degrees Celsius stretch and shrink the deck by meters, straining every joint and bearing. And above all, the bridge must carry the live load of hundreds of high-speed trains each day, each one a moving shockwave of force. Every kilometer adds another layer of risk. The longer the bridge, the more ways nature can find a weak point. Engineers had to face not just one hazard, but a tangled web: soft ground, sinking land, earthquakes, storms, water, ships, heat, and the weight of relentless traffic. The solution would demand new thinking at every step. Only by stacking defenses, foundation by foundation, could the bridge hope to survive where, by all rights, nothing so ambitious should ever stand. Li Changhe stands at the edge of the Yangtze Delta, boots sinking slightly into ground that looks solid but cannot be trusted. Beneath the surface, layers of silt and clay run hundreds of meters deep, deposited by ancient floods and tides. This is the greatest threat to the world's longest bridge, not wind, not water, but the slow, invisible movement of the Earth itself. To anchor a structure stretching 164.8 kilometers, engineers must reach past the softness. Each pier sits atop a forest of concrete piles, driven 50 to 70 meters below the marsh until they bite into stable sand or gravel. Some piles are as long as a 20-story building laid on its side. The load of the bridge is transferred downward, bypassing the unreliable upper layers and settling on ground that has not moved for millennia. But even this is not enough. Before a single span rises, the Earth must be taught to carry weight. Months before construction, teams haul in tens of thousands of tons of fill, stacking soil into low mountains along the road. This pre-loading, or surcharge, compresses the ground, squeezing out water and forcing the clay to settle ahead of time. Sensors record every millimeter of movement. In some places, the land sinks by more than half a meter over the course of a year. Only when the readings level off do workers strip away the fill and begin building the real bridge, confident that future settlement will be slow and predictable. The process is painstaking. Each foundation is mapped, measured, and checked again. If a single pile misses its mark, or if the ground shifts unexpectedly, the entire span above could twist or crack. Li Changhe's team spends years studying the soil, drilling test cores, and running simulations. Their goal is not just to build, but to outlast the river and the ground beneath. The bridge begins not with steel or concrete, but with a battle against the Earth itself. A battle won meter by meter, pile by pile. The Yangtze Delta's soil is a shifting puzzle, layers of silt, clay, and sand that resist easy solutions. Even after deep piles reach solid ground, the space between each foundation must be made strong enough to carry the weight above. To achieve this, engineers create a hidden grid of stone columns beneath the surface. Each column, about 0.8 meters in diameter, is formed by driving crushed rock deep into the soft clay. These columns are arranged in a tight lattice, sometimes spaced just 2 to 3 meters apart, forming a network that stiffens the entire ground matrix. The result is a reinforced base that spreads the load evenly, preventing the bridge from settling unevenly or tilting over time. In areas where the soil remains especially loose, vibrocompaction is used. This technique drives a vibrating probe into the ground, shaking the sand and silt into a denser, more stable mass. The process is repeated in a pattern, ensuring that no pocket of weakness remains. Grouting adds another layer of defense. Engineers inject cement slurry into the earth, filling gaps and binding loose grains together, especially around the toes of piles and beneath critical piers. This reduces the risk of water seepage and boosts the strength of the weakest layers. Spacing between piers is not left to chance. On the Danyang, Kunshan Grand Bridge, most spans measure between 32 and 44 meters, a range chosen after thousands of soil tests and cost calculations. Shorter spans mean more piers and higher cost, but longer spans demand heavier girders, which can overload the ground. The 30 to 60 meter rule is a balance, tight enough to limit bending and settlement, but wide enough to keep the bridge economical. Each decision is checked by sensors and survey plates, which monitor settlement in real time and flag any movement outside the safe zone. These ground improvement tactics are not visible from above, but they are the reason the viaduct can stretch for 164.8 kilometers without sagging or cracking. The bridge's survival depends on a matrix of stone, sand, and grout, an invisible armor that lets the superstructure rise and carry the weight of high-speed trains season after season across land that was never meant to hold such a burden. Every span of the Danyang Kunshan Grand Bridge moves, flexes, and breathes with the world around it. Temperature swings of 40 degrees Celsius can stretch the deck by more than a meter across its full length. To manage this constant drift, engineers rely on pot bearings, each capable of absorbing up to plus or minus 200 millimeters of movement. These bearings act like giant sliding pads, letting the bridge expand and contract without cracking or jamming against its supports. At every pier, expansion joints create a controlled gap, wide enough to swallow the daily push and pull of steel and concrete. But movement isn't just about heat. The Yangtze Delta is famous for storms that can whip up winds strong enough to rock a train off its tracks. The bridge's aerodynamic profile is sculpted to slice through these gusts. Its deck is shaped with subtle curves and edges, breaking up the airflow and stopping dangerous vibrations before they can build. Underneath, fairings and diaphragms channel the wind, reducing the force on every span. Even so, wind can set a bridge humming like a tuning fork. To counter this, tuned mass dampers are installed inside the structure. Each damper is precisely calibrated, tuned to frequencies between 0.9 and 2.2 Hz, the same range as the bridge's natural sway. When the wind tries to set the deck in motion, the dampers swing in opposition, sapping energy and keeping the bridge steady. Li Changhe, the project's wind specialist, describes it as a kind of invisible orchestra, every bearing, joint, and damper working in harmony to let the world's longest bridge shrug off storms that would threaten any ordinary span. Every record-length bridge is designed with the expectation that something, someday, will go wrong. The Danyang Kunshan Grand Bridge is no exception. Instead of relying on a single line of defense, engineers build in redundancy at every level. Each span, each pier, and each joint is part of a network that can reroute loads if damage occurs. If one section is struck by a ship or weakened by settlement, the bridge's segmented construction allows forces to bypass the affected area. Main load-bearing elements are sized to withstand 2 to 3 times the maximum expected stress. This margin, known as the safety factor, is not a luxury. It is a requirement for survival across 164.8 kilometers of shifting ground and relentless traffic. Corrosion is a constant adversary. To combat rust, every steel surface is coated with advanced paints and galvanization, while cathodic protection systems run electrical currents to arrest the chemical reaction before it can eat through the metal. These systems are checked on a strict schedule, often every few months, with maintenance teams recording voltage, current, and any signs of breakdown. Drainage channels and waterproof membranes keep water from pooling at joints and bearings where corrosion can start unseen. Fatigue is another silent threat. High-speed trains crossing the bridge create millions of cycles of stress each year. Microcracks can form in welds, bearings, and cables, too small to spot at first, but capable of growing with every passing load. Inspectors like Zhang Wei walk the length of the bridge, tapping welds and scanning surfaces with ultrasonic devices. Every weld and joint is logged, tracked, and compared against previous inspection cycles. If a crack is found, it is drilled out or reinforced before it can spread. Inspection intervals are not left to chance. Critical elements are checked as often as every 6 months, with less stressed components on an annual schedule. This routine, layer upon layer of checks, coatings, and built-in backup, ensures that the bridge does not depend on any single component or flawless performance. It is a survival strategy built on the expectation of failure and on the discipline to catch small problems before they become disasters. A bridge that stretches for 164.8 kilometers cannot rely on memory or routine. Instead, it is watched by a digital sentinel, over 1,200 sensors embedded throughout its length, forming a nervous system that never sleeps. Strain gauges measure the flex of steel and concrete as each high-speed train races overhead. Accelerometers and tilt sensors detect the faintest tremor, whether from distant earthquakes or the subtle shift of settling ground. Displacement meters track how much each span expands or contracts with the seasons, and corrosion sensors monitor the condition of hidden steel, alerting operators before rust becomes a threat. All this data flows into a central command room, where the bridge's operations director and her team read live dashboards of numbers and graphs. If a sensor detects unusual movement, perhaps a pier settling faster than expected, or a joint flexing out of range, the system triggers an alert. Maintenance crews are dispatched long before a problem becomes visible to the naked eye. On a typical week, drone flights scan the viaduct from above, capturing high-resolution images for comparison with last month's inspection. Specialized trains equipped with cameras and ground-penetrating radar roll along the rails, checking for cracks or voids beneath the surface. Every anomaly is logged, tracked, and, if necessary, scheduled for repair. This is not just routine oversight. It is predictive maintenance, an approach that turns every sensor reading into an early warning. The bridge's survival depends not on luck or hope, but on a constant stream of information. In the world's longest bridge, vigilance is engineered into every meter, every day. Operational rules for the world's longest bridge are set with precision. Speed limits, lane controls, and crosswind protocols are enforced automatically, with real-time data from more than 1,200 embedded sensors. When wind speeds rise above 130 kilometers per hour, traffic is slowed or halted, far less often than ferries are sidelined by fog or floods. Emergency laybys appear every few kilometers, and escort vehicles guide oversized loads, ensuring that even during storms or seismic events, safety remains uncompromised. The cost of building the Danyang Kunshan Grand Bridge reached $8.5 billion, a figure that once drew skepticism from critics. But transport economists point to the numbers that matter over time. The bridge delivers over 99.9% uptime each year, compared to ferries that lose up to 30% of operational hours to weather and maintenance. Scheduled closures are rare and brief, planned well in advance based on predictive maintenance models that draw from decades of sensor data. Over a 50-year horizon, the bridge's uninterrupted service saves millions of hours in travel time, reduces accident rates, and supports a high-speed rail network that moves tens of millions annually. The value is not just in the steel or concrete, but in the stacking of 10 distinct domains: ground improvement, deep foundations, seismic isolation, aerodynamic shaping, redundancy, corrosion defense, fatigue management, real-time sensing, predictive maintenance, and traffic control. Each one adds a margin of safety, reliability, or efficiency. A transport economist puts it simply: a bridge looks expensive until you add up every storm-canceled ferry, every hour saved, and every shipment sped up over 50 years. It shouldn't stand until you see how every meter is engineered to let it. At 164.8 kilometers, the Danyang Kunshan Grand Bridge stands as the world's longest, supported by over 50,000 deep piles and monitored by more than 1,200 sensors. The documentary has shown how engineers responded to soft soils, typhoon winds, seismic zones, and relentless traffic, using solutions like 70-meter piles, pot bearings with plus or minus 200 millimeter movement, and inspection cycles measured in weeks, not years. Documents confirm these marginal gains were not a luxury, but a necessity, each one addressing a failure mode that multiplies with distance. Yet not all data is public. The full maintenance logs and some stress test results remain classified by local authorities. Still, the facts are clear. Across 5 decades of service life, the bridge's uptime and safety records have outperformed ferries and tunnels. The lesson is simple. Record-breaking spans do not cheat physics. Instead, they turn every threat into a checklist and every meter into an engineered answer. It shouldn't stand until you see how every meter is engineered to let it.